Okay, what you're asked to do can be pictured like this. Okay, first of all, one thing I should have added, I should be less than or equal to n. Okay? Now what does that do? First place, you can see that this expression, if I is less than or equal to n, is in between negative L over 2 and L over 2.
Did you mean for there to be a 1/2 added to the I?
All right. Uh-oh. It's negative L over 2 plus L over n. No?
It's
You have negative L over 2 plus I plus 1/2 times L over n.
Yeah, you're right. Okay?
Yeah, okay.
And that really doesn't make any big difference, but I'll explain the reason for that in a minute. Okay? So, if I is less than or equal to n, then it's really easy to see that this is less than or equal to L over 2. Right? If I is equal to 1, I'm going to change that expression. Again, it doesn't make a huge difference, but it should have been I minus 1/2. So you might make that correction. Okay? If I equals 1, then you have L over n times negative 1/2, right? Okay? So adding L over 2n, adding L over 2n to negative L over 2 gives you, if n's a big number, gives you something just a little more than negative L over 2. If I equals n, then this becomes just L, right, minus 1/2 n. If n's a small number, that's going to give you a number very close to L over 2. But both numbers within this interval. And you want to work that out. You've done enough sequences in your calculus class and analysis of sequences with indexes and so forth. Presumably you've done this. I'm pretty sure you have. That you can understand this notation and how it's related to intervals, because that's where we're headed. Okay? So what you've essentially done is this divides the interval from negative L over 2 to L over 2 into n sub-intervals. That looks like sob intervals, and sometimes they'll make you want to do that. Okay? And these are the midpoints. I really want to draw all those midpoints, but what the heck, it doesn't take that long, okay? So you might give that a little thought, but right now, there's the coordinate. Here's the point x, y. So tell me how we're going to get the field at this point.
R vector.
Going to do our r vector. What's its magnitude going to be?
Conic squared. X square root.
Okay, well, we got our r vector, right? Okay. And r equals x minus negative L over 2. I don't know if it's a board or the chalk, but I think it's a chalk. Plus L over n times I minus 1/2 times I, do I have enough parentheses? No. Plus yj, right?
Okay.
And then the electric field at that point, we can write down pretty instantly if we understand what we just did before. You know, all this just replaces the negative L over 2 or the positive L over 2, whichever one we want. So the and let's call that R sub I, because what that's actually going to represent is a charge at the middle of an interval. I could be anything from 1 to n, so you could have, this could represent any interval. Okay, so EI is what? Oops, wrong column. Well, what's the charge at this point? Well, we're dividing our charge up into n parts, okay? So I could also say charge Q over n in each subinterval, okay? Okay, so we have this. I've just distributed the negative sign here. Hopefully I did that right. Okay? And then we're going to have what? X plus L over 2 minus L over n times I minus 1/2 squared plus y squared to the 3/2. That's going to be the electric field, right? From the ith component. So the total electric field, which I'll write now in function notation, electric field at the point x, y, is, I didn't want to write the sum there, I want to write the summation first. I want to write, okay. I want to factor out the kq over n. And then it's just times the sum of all these. I don't have time to write all this out, but the sum of that, right? Okay. Well, where do we go from here? You don't want to add that up because you don't know what n is. You can't anyway. You can take a limit as n approaches infinity. Okay? And you would get an integral. But let's do the integral the way we're used to doing an integral. Okay? So we're going to go to where we have the whole x-axis. We're going to let lambda equal the charge per unit length. And we're going to take a typical increment delta x. With an x star. And we're going to write out the contribution to the electric field at the point x, y. So, I'm going to just give you a minute. Don't bother copying everything down. Tell me what the R vector is going to be. Okay? That's your key. And tell me what the charge inside this increment is.